The new section is going to talk about solving homogeneous linear systems with constant coefficients. For example, if you were given what dx dt equals and what dy dt equals, notice that the coefficients are all constants, 3, 1, 1, and 3. Now basically, you solve this using eigenvalues and eigenvectors. You want to make up the characteristic equation. The characteristic equation, well, first let's talk about what the matrix A would be. For dx dt, just put down the coefficients of x and then y in the first row. For dy dt, put down the coefficient of x and then y. That's matrix A. When you get the characteristic equation, we want to compute the determinant a minus lambda times I and set it equal to 0. Well, we know what A is. It's 3, 1, 1, 3 minus lambda times I. Well, that's I. Multiply it by lambda, and you just get lambdas on the diagonal and zeros off the diagonal. And so you're going to have a minus lambda I. And it equals to 3 minus lambda, 1, 1, 3 minus lambda. Basically, all you do is you write down the term matrix A, that's matrix A, and just take away lambdas from the diagonal. And we want the determinant of this, which is that product, 3 minus lambda squared, but I'll write it as lambda minus 3 squared. Remember, a minus b squared is the same as b minus a squared. Why is that, you ask? Well, here's a very quick proof. We know that a minus b is b minus a with a negative in front. Call it a negative 1. So if you square the left side, you can square the right side. So when you have a product being squared or cubed or whatever, you can raise each factor. Raise each factor first to you can square each factor and then multiply the results. So we get 1 times b minus a squared, which is b minus a squared. So this really does equal that. And why did I bother writing lambda minus a squared? So when I FOIL it out, it's a bit friendlier. Okay. Minus that product. And we want this to be 0. Well, if this, you can FOIL this out, or you can say, well, if I subtract those two quantities and I get 0, then I can just write down the two quantities and put an equal sign in between. Because this has to be 1. Because 1 minus 1 is 0. Okay, what do you square to get 1? Answer is plus or minus 1. Lambda minus 3 is either 1 or lambda minus 3 is negative 1. And you all know that 4 take away 3 is 1. So that's one value. And you know that 2 take away 3 is negative 1. If you don't know, there's lambda. Take away 3. 1, 2, 3. And you end up at negative 1. So that's 0, that's 1, and that's 2. So now we have the two values of lambda. Just for the record, another way to have solved this is to actually square this. You get lambda squared minus 6 lambda plus 9 minus 1 is plus 8. And when you factor that, you get lambda take away 4 times lambda take away 2. And since it equals 0, lambda is 4, or it's 2. So we got the same results over here. So there are two different ways to do this. So now that, and these values here are called eigenvalues. Now we want to find the corresponding eigenvectors. So we've just learned that these are the two values for lambda. Now we want to solve this. A take away lambda I times some vector k. K is k1, k2. And we want this to be 0. Now if lambda is 4, I'll do it down here. This here is A, 3, 1, and then 1, 3. And we want to take away 4 from each of the diagonal entries. So this here is what we get. And this value here was 3. I don't know why I put down negative 3. And 3 minus 4 is negative 1. So we get this here, which is negative 1, 1, 1, negative 1, times k. Now, why is k, k1, k2? Because each row has 2 entries, that is 2 columns. So I had to put 2 columns here. And I want to get the 0 vector. I'm going to get 0, 0, the 0 vector. Well, that just means I want to solve this homogeneous solution. Well, if I just add row 1 and row 2, this is row 1, and row 2 is going to be all zeros. So it's in what's called the reduced row echelon form. This says that negative k1, this equation says negative k1 plus k2 is 0. Bringing that to the other side, it says that k2 is equal to k1. k2 is equal to k1. So you let k1 equal some nice number. Let k1 equal 1. Well, that implies that k2 is also 1. Because whatever k1 is, k2 is equal to that. So now k is equal to k1, k2, 1, 1. Now we have one of the vectors. We'll call this lambda 1. And lambda 1, lambda 2. So lambda 1, that gives us k1. K bar 1. The x1 is going to be 1, 1. It's going to be 1, 1. And then it's e to the lambda t. That is one value. So associated with lambda 1 equals 4, we get that x1 is 1, 1 e to the 4t. Now, let's do everything we just did again, but this time Lambda is now 2. So this is A, 3, 1, 1, 3, but since lambda is 2, I take away 2 from the diagonals, and what I get is 1, 1, 1, 1. So I have 1, 1, 1, 1. Now it's really, case of 2. And we want this here equal to the 0 vector. And we're going to solve for big K2. Well, subtracting, just do row 2 minus row 1. You get a row of zeros in the bottom, and you're done. This says that K1 plus K2 is 0. K1 plus K2 is 0. Bring that to the other side. K1 is negative K2. The right side is more complicated, so I'll pick a value for K2. Let K2 equal 1. Well, then K1 is negative whatever K2 is, which is 1. I know that from here. Okay. So capital K, vector K2 is K1, K2. So that's where K equals. Now once you have K, you can get X2. K2 equals. It's going to be that vector, K2, times e to the lambda is 2, 2t. Negative 1, 1, e to the 2t. And I failed to write something a little bit important. I want to say that x2 equals that. Alright, so now we have x1 and we have x2. I'm going to erase most of this, and then I'm going to write down the general solution. X is equal to c1 x1 plus c2 x2. That is c1 times x1, which is 1, 1, e to the 4t, plus c2 times x2, which is right here. Negative 1, 1, e to the 2t. That's the vector x. These are also vectors. Now, what does it mean that x is equal to that? Well, with respect to the initial conditions, we know that x prime is equal to a 3, 1, 1, 3 times x. If you multiply this by this, you will get the derivative. And for the record, the derivative will be c1 times, well, this is really 1 times e to the 4t. The derivative will be 4 e to the 4t. Same for the bottom. It will be 4 e to the 4t. Plus c2. Negative 1 times that will be negative e to the 2t. The derivative will be negative 2 e to the 2t. 1 times that, the derivative will be 2 times e to the 2t. And we actually worked this out. That's exactly what we're going to get. And let us actually do that. We have c1 times, I'll actually write it down, e to the 4t, e to the 4t. I just multiplied the 1's by e to the 4t. Plus c sub 2 times negative e to the 2t, e to the 2t. Okay, so you get. Now, it's this plus that in the second bracket. So I can distribute when I multiply the matrices. The C1 stays in front. When I multiply this row by this, I will get 3 e to the 4t plus 1 more e to the 4t. I'll get 4 e to the 4t. And the same thing with the bottom, except I'll add 1 e to the 4t plus 3 e to the 4t. I'll still get 4 e to the 4t. And the C1 factored in front, plus the C2 can come in front. When I do this times that, get negative 3e to the 2t plus 1e to the 2t. That gives me negative 2e to the 2t. When I multiply the 1, 3 by this matrix, I get negative 1e to the 2t plus 3e to the 2t, which is positive 2e to the 2t. If you notice, I got exactly what I said x prime would be. I got exactly this. These two are exactly correct. Okay, that was a check. It had nothing to do with this problem. If you have time on an exam or homework, check it. Make sure you got it right. But the bottom line is, here's the answer. Initial problem says find x. So verifying is a good thing to do. That way you know you're right. Isn't it good to know that you're right? Try another one. dx dt is negative 5 halves x plus 2y. And dy dt is 3/4 x minus 2y. So A, I'll put dx dt's here, the coefficients of dy dt here. First column is x and then y. So it's negative 5 halves 2. Negative 5 halves and 2. In the second row, dy dt is 3/4 x, negative 2y. So now we want a minus lambda I. That is, we take away lambda from the diagonals. As easy as that. Just take away lambda. So that is no longer a on top here, but rather a minus lambda I. And we want the determinant of this, which will be this product. Now, both of those term factors are, we can factor out a negative here. I can say it's negative 5 halves plus lambda times this. I can factor out a negative 2y plus lambda. The negative times the negative is positive. That is, this is just the same as this times that. And when I say this times that, I'll write it. I'm going to write the lambdas first. Minus that product. 3/4 times 2 is 3 halves. And that's what we get. Now we want to see when this equals 0. Because we want this to equal 0. So you get lambda squared plus 5 halves plus 2. Now think of the 2 as 4 halves. So that's 9 halves. You add those two numbers, you get the number of y's. Plus, you multiply these two numbers. 5 halves times 2 is 5. Minus 3 halves. It's still 0. Well, 5 is 10 halves. And we're taking away 3 halves, so we really have 7 halves. 5 minus 3 halves is 7 halves. Now, there's lots of ways of doing this. Already did it. Let's just write down the answers. Turns out that x1 is -1 and the other root is -7 halves. So those are the two that's the solutions to the characteristic equation. By the way, this here is the characteristic equation. It's this equals 0. But this is what's over here, and it equals 0. That's the characteristic equation. And these here on the bottom are the eigenvalues. So what we want to do at this point is to find the eigenvectors. Lambda 1 is -1, and lambda 2 is -7/2. And we're going to keep these two values and find the vectors associated with them. So at this point, we do just like we did last time. We're going to deal with lambda 1 being -1. And we want to solve a minus lambda I times vector k is the 0 vector. So here's our a minus lambda I, where lambda is -1. That means we're adding 1. Taking away -1 is you're adding 1i. That is, you're going to have -5 halves, 2 3/4, and -2, no y, excuse me, -2 plus 1, or -2, that's 8. And we're going to add 1 to everything on the columns. Of course, I wrote the 1 that way because what I'm adding it to had a 2 in the bottom. So we have -3 halves, 3/4, 2, and -1. So -3 halves, 2, 3/4, and -1. And we want to augment that with 0. We want to solve this system of equations using matrices. Now, I noticed that if I double the second row is R2, I double it. So I'm not doing anything to the first row. I didn't put anything there. You get 3 halves and -2. Well, if you happen to add row 1 and row 2, row 1 I'm not doing anything to, and then row 2 gives me zeros. You add the additive inverses. You add them, you get all zeros. Okay. Okay, well, this tells me, we'll call the variables k1 and k2. -3/2 k1s is plus 2k2 is 0. Bringing that to the other side, we get 2k2s is equal to 3 halves k1s. It's very friendly to divide the left side by 2. It is more friendly to multiply the right side by a half. So we get k sub 2 is 3/4 k1. Okay, so we'll let k1 equal 4. So 3/4 times 4, the 4's will cancel, and you get 3. That's why I multiplied by 4. So K2 is equal to 3. So K is equal to K1, K2. I'm going to call that K1, associated with lambda 1. So we now know that x1, well, it's K1 times e to the lambda t. That's x1. Now we do this all over again, where lambda is negative 7/2. Lambda 2 is negative 7/2. So we have negative, and copying this over here, a minus lambda I, and we'll augment that with 0. We have negative 7/2 minus this number, that means we add 7/2 to 3/4, and negative 2 plus 7/2. Well, since we're in addition, the bottoms are both 2, we just add the tops. Negative 5 plus 7 is 2. Over 2 is 1. That 2 stays 2. The right sides are 0. That's 3/4. I'll think of this negative 2 as negative 4/2. You add 7/2, you get back 3/2. Now, if you're slick, you notice that if you double this number, you get that number. And if you double this number, you get that number. That is, when you subtract those two, you're really going to get 0. You're really going to get 0. If you don't see that, I'll multiply row 1 by 3/4. So I have 3/4, multiply that by 3/4, you have 3/2. And then you say, oh yeah, this guy is right, this guy is right. That second row is going to become zeros. The first row I can leave as 1, 2. Okay, so this tells me that K1 plus K2 is plus 2 K2s is 0. Bringing this over, it tells me K1 is negative 2 K2s. So let K2 be 1. And then K1 is negative 2 times 1, which is negative 2. That tells me K sub 2, the vector, is K1, K2. So X sub 2 is K2, negative 2, 1, times e to the lambda, negative 7/2, t. And now I can write down what vector x is. Vector x is a linear combination of x1 and x2. The constant multiple of x1 plus the constant multiple of x2. Those are vectors. And it's C1 times matrix 4, 3, e to the negative 1t. And just e to the negative t plus C2 times x2, which is negative 2, 1, times e to the negative 7/2t. And there's your answer. And please understand that it's the answer to this question. The answer to that question. This gives us the A. The A is fixed. The question is, what should x be, so when you multiply a by x, you actually get the derivative of x. That's what we're solving for. No fun or anything learned in knowing how to do everything that I just showed you, but not knowing that you're solving for that x. The a is given from here, and we want to find x. Now, these last two problems we've done, when we found the characteristic equation, they had two real distinct roots. Well, what happens if a root gets repeated? And that's what's going to happen with this problem. Suppose you have that, and dy dt is, say, 9x minus 3y. So we want to find the characteristic equation, a minus lambda I. Well, and in fact, we want it to be a determinant. We're going to set it equal to 0. Well, here is a, 3, 1, and then 9, negative 3. And all you do is take away the lambda from the diagonals. If I want to multiply this by that, but I can multiply each of them by negative 1, because 3 minus lambda times negative 3 take away lambda is surely the same as negative 1 times negative 1, which is 1 times that. And I choose to multiply this with that. This gives me lambda take away 3. And I want to multiply this with that, which gives me 3 plus lambda, or lambda plus 3. So lambda take away 3, lambda plus 3. Minus that product, which is 9. So you have lambda, this will give you lambda squared take away 9. And I do have one silly error. There's a negative 1 there, so this shouldn't be 1, it should be negative 1. So when you multiply those two, you get negative 9. And you have to take away a negative 9, which really means you add 9. So what I've written down here was just this. Plus 9 is lambda squared, which is 0. That means when it comes to the eigenvalues, we have a repeated one. This really means lambda times lambda equals 0. So either that's 0 or that's 0. Repeated. You had one root. You should have gotten 2, in fact, because this is a quadratic. It's the second degree. So if lambda cubed equals 0, then I would say that there's 3 roots, and they're all 0. Alright, so what happens when a root is repeated? What happens then is you want to solve the following. The first thing you want to solve is just like before. A minus lambda I times k is equal to the 0 vector. And you also want to solve a minus lambda I times vector p, but this time it's not homogeneous. It equals to k. Now, the nice part is, if lambda is 0, 0 times I, 0 times this, is going to be the 0 vector. And a take away lambda I, that is a take away the 0 vector, is just a. This is just a. this is just A. And we want to solve those two equations. Now, we need to be smart in doing this one. Well, actually, that won't work. Alright, so we have to do this one first. We don't know what K is, otherwise I would do both of these at the same time. So let's find out what K is. So we have A, 3, negative 1, 9, negative 3, augmented with 0. Augmented with 0. Now, you should see that the second row is just 3 times the first row. That is, if you triple the first row, this will become 3, negative 3, sorry, it will become 9, negative 3, 0. Exactly what row 2 is. So if you just take away row 2, then you'll have a row of zeros. The first row doesn't change. And now we can solve this. This tells me that 3 times K1 minus K2 is 0. Remember, that's the K1 column, that's the K sub 2 column. Bringing that over tells me that K2 is 3 times K1. So you pick a value for K1, you triple it, and bingo, you have K2. So let K1 equal 1, and that will imply that K2 will be 3 times 1 or 3. So big K is equal to K1, K2. So x1 is equal to 1, 3 times e to the lambda, which is 0t. And e to the 0t is 1, so you just get 1, 3. So x1 is 1, 3. Okay. So we want to solve this here. But now we know that k was 1, 3. So we want to do AP equals 1, 3. A times vector P is equal to the vector 1, 3. But A is 3, negative 1, 9, negative 3. And it equals to K, 1, 3. If you triple the first row, you'll have 3 times 3, 3 times negative 1, and 3 times 1. And if you just add row 2, sorry, if you take away row 2, this is row 2. You take it away, in row of zeros. So we have 3, negative 1, 1, 0, 0, 0. Well, this tells me now this is P, P1, P2. P1, P2. So 3 times P1 minus P2 is equal to 1. So you let P2 equal something that will make things nice. Or what you do is maybe we'll let P1 be 1. So then this is 3. And you should know what to take away from 3 to get 1. The answer is 2. 3 take away 2 is 1. So P is 1, 2. So now we're in a position to write down what x2 equals. Now x2 is a little bit harder than before. x2 is going to be, remember what k was? It's going to be k1. It's going to be, naturally we called it k, excuse me. It's going to be k times t. It's going to be k times t times e to the 0t. So it's just like what we got for x1, except we multiply it by t. Plus, and now we're going to take p, and we are going to multiply p by e to the lambda t. And of course, we don't need either of those. The x of 2 is just 1, 3t plus 1, 2. That is x2. And that's the answer. Or now we have enough information to write down the answer. X is c1 times x1, and x1 is right here. 1, 3 times e to the 0t, which is just 1, 3, plus c2 times this. 1, 3t plus 1 half, or 1t. And that's what x is. Again, it's the solution to this. If you multiply the matrix A by this x, no matter what C1 and C2 are, you will actually get the derivative. Now, of course, x prime will be, well, the derivative of 1 is 0, the derivative of 3 is 0, you're going to get the 0 vector, plus C2 times, well, the derivative of 1t is 1, the derivative of 3t is 3, plus the derivative of 1 is 0, derivative of 2 is 0. So I have 1, 3, and I'm adding 0, 0, so I just get 1, 3. So that's the derivative. If you multiply A by this mess, you're gonna get x prime. You're gonna just get that. It's pretty neat. Pretty neat. So that was an example where we had one repeated root, or we had a repeated root. Alright, so now we're going to be given an equation in different format. It still means the same. We still want to find out what x is. 5, negative 4, 0, etc. Now, just for the record, this came from dx dt 5, well, I take that back, dx dt is equal to 5x minus 4y plus 0z. Row 1 in the matrix above this line. And dy dt comes from the second row of this matrix. 5x plus no y's plus 2z's. And the third row corresponds to dx dt is 0x's, so I won't write it, plus 2y's plus 5z's. Okay, if you were given this, it really means this. Solve for x. Remember, big X is little x, little y, little z. Okay, so we're going to do this the same way as always. We want to find a minus lambda I. The determinant, and we're going to set it equal to 0. Well, that just means well, it's not the 0 number. That just means that we write down A And on the diagonals, we take away lambda. And 0 take away lambda is just negative lambda. If you want to calculate the determinant of a 3 by 3 matrix, the best thing to do is to repeat the first two columns at the end. This is the first column that's repeating, and this is the second column. And the determinant is going to be as follows. It's going to be this product, which is negative lambda times 5 minus y times 5 minus, I meant to say 5 minus lambda 2 times, plus this product, which is 0, plus that product, which is 0, minus these products. That product is 0. 2 times 2 is 4 times 5 minus y, plus negative 4 times 5 minus y. Well, if you have 4 of these and you take away 4 of these, this is 0. That is, you just have 0 is negative lambda times 5 minus lambda squared. That means either that's 0 or this is 0. Or 5 minus 5 is 0. 5 minus 5 is 0. So lambda should be 5. But that's a repeated root, because it's really negative lambda times 5 minus lambda times 5 minus lambda. This factor is 0 when lambda is 0. This factor is 0 when lambda is equal to 5. And that factor is 0 when lambda is equal to 5. Lambda equals 5 came up twice. Okay, so let me just write down the lambdas. Lambda is 0 and lambda is 5. Call lambda 1, lambda 2. And lambda 2 came up 2 times. So I'll have to play the same game with that lambda that we did for the last problem. But lambda equals 0 just came up 1 time. So we'll do it like we did it when we had distinct roots, non-repeated roots. That is, we want to do a minus lambda I times k is equal to 0. Thing is that if lambda is 0, 0 times the identity matrix is their 0 matrix. And A minus the 0 matrix is just A. This is just A. So we have 5, negative 4, 0, 1, 0, 2, 0, 2, 5. And we augment it with the 0 vector. And we can interchange row 1 and row 2, for example. Get a 1 up there. 1, 0, 2, 0, 5, negative 4, 0, 0, and 0, 2, 5, 0. Now, I want what's below this to be 0. I want what's above it to be 0 as well, but there is no above. Well, this is 5, and I can get that to be 5. I'll keep row 1 the same. That puts the 5 here. And I'll multiply row 2. I'll keep the same, excuse me. And row 1 I'll multiply by 5. Well, that's going to be a 5, and that's going to be a 5. To get 0, I'll subtract. That already is a 0. So now, here is row 2. Here is 5 times row 1. And if I subtract, I get that. And I'll even divide it by 2, which will give me 0, divided by negative 2. 0, 2, 5, 0. So row 1 did not change. Row 2 became this. And row 3 did not change. Now, I'll just do row 3 minus row 2, and that will do it. Since row 2 and row 3 are exactly the same, if you were to subtract them, you'll get 0. And this is not a linear algebra class, so I'm not teaching how to row reduce matrices. I'm rushing through it. Okay. This is K1 and K2 and K3. The first line tells me K1 plus 2K3 is 0. The second line tells me that 2K1 plus 5K3 is 2K2 plus 5K3 is 0. K3 is in both of them. I'm going to solve for the other letters, K1 and K2. I bring that over, and I get that K1 is negative 2K3. If I bring that over, I have 2K2s is negative 5K3. But I'll divide by 2. Now, I'm going to pick at random a value for K3. But I would love for 2 to go into it. Well, 2 goes into 2. I'll let K3 be 2. So then K2 will be negative 5 because the 2's cancel. And K1 is negative 2 times 2, which is negative 4. So due to lack of space, I'll write K here. K, since the subscript is 1, big K1 is little k1, little k2, little k3. And of course I said k3 was 2, but I put 3 by error. So that tells me that x1 is k1, negative 4, negative 5, 2, times e to the 0t. But e to the 0t is 1. I don't need to put that. So I have x1. Now, we do this all again, but we do it for lambda 2, which is 5. Now, please remember that this is a repeated root. So we need to solve a minus 5i times k is equal to 0, and a minus 5i times p is equal to k. So before we can solve this one, we need to know what k is. That is, we're going to do this. So I just take away 5 from the diagonal entries. Take away 5 from those. And everything else stays the same. 0 minus 5, 5 minus 5. Augment this with 0. I'll interchange row 1 and 2. This will become row 1. And so this one up here. And when I bring this one to row 2, I'm even going to divide by negative 4. And row 3, I'll divide by 2. Now, if 2 rows are exactly the same, like row 2 and 3, upon subtraction, you have 0. Now, if a row, like row 2, is all zeros, except one entry is a 1, it can kill off every entry in other rows above or below the 1. I can kill off that negative 5. Why? I just multiply this row by 5, and I get 5. Now when I add, well, when you add a 0, it doesn't change anything. But that becomes 0. That becomes 0. And like I said, it doesn't change. 1 plus 0 is 1. So I got 1, 0, 2, 0. And the variables are k1, k2, and k3. So 1k1 plus no k2s plus 2 k3s is 0. That means k1 is negative 2 times what k3 is. The second row says that k2 is equal to 0. Okay. So I'll let k3 be some number. Let k3 equal 1. Well, that implies that k1 is negative 2 times 1. Negative 2. So there it is. So again, I ran out of space, so let's sneak it in here. k2 is k1, k2, k3. k2 is negative 2, 0, 1. That is k2. Okay. So I solved this. Now I have to solve this one. The only big difference is instead of the right side being 0, it's now k, which is negative 2, 0, 1. Negative 2, 0, 1. And we solved this. Okay, so now if I divide the first row by negative 2, get 0, 2, 0, 1. The second row I won't change. The third row I won't change. Well, I already see a row of zeros. The first and third row is 0, so I'll subtract. Sorry, the first and third rows are the same. I'll subtract, I'll get 0. Now, I want to get that to be a 0. And I'm going to use row 1. If I multiply row 1 by 5, I will get 0, 10, 0, 5. And if I multiply row 2 by 2, I'll get 0, negative 10, 4, 0. And if I add, I get that. So that's going to become the new row 2, and row 1 is this. And the unknowns are P1, P2, and P3. The first equation tells me that 2 P2s is 1. Oh, that means P2 must be a half. The second row tells me 4 P3s is 5. So P3 is 4/5. And P1 can be anything. Now, I'm concerned about that statement. Let's not rush into this. If I multiply this row by 5, I get 0, 10, 0, 5. If I multiply this row by 2, I get this. And when I add, I get 2, 0, 4, 5. So that 0 should be a 2. Sorry, folks. Okay. So the second equation reads 2p1 plus 4p3 is 5. Well, if I let p3 be 1, well then this is 4. This 4 times 1 is 4. So this must be 1. 1 plus 4 equals 5. So 2p1 must be 1, which means p1 is a half. So now I have big P. It's P1, P2, P3. That's P. We'll call it P2 because it's associated with lambda 2. Okay. Now I am in a position to write down x2. I can now write down x2. X of 2 is going to be k1 from when lambda was 0. C1 k1 times t e to the 5t, because lambda is 5, plus c2 times p2 times e to the 5t. That's x2. And x1 is right here. So the solution is x1, c1. Actually, I take back one thing. Sorry. That's x2. This is what x2 equals. So big X is equal to c1 times x1, where this is x1, plus c2 times x2. I'm just copying down x2. There's your answer. That was the second problem where we had repeated roots. The first case, we just had one root, it was repeated. In this case, we had two roots to the characteristic equation. When lambda was 0, its multiplicity was 1. But when lambda was 5, the multiplicity was 2. That's why we have a t e to the 5t and just an e to the 5t. Next cases are going to be when the roots are complex. Either you have distinct root. When you have real roots, either they're distinct, that is, the multiplicity is 1, or the multiplicity is 2 or more. In the last problem, one root was multiplicity 1, the other root was more than 1, it was 2. Or you can have what I just described with complex roots. And if you had, well, let's use lambda. If you had lambda minus 1 times lambda minus 2 squared times lambda squared plus 4 equals 0, well, lambda would be 1, lambda would be 2, or lambda would be plus or minus 2i. We had a single root. We had a double root. Let's make that 12. 12 is a double root. And we had complex roots. Okay, so let's talk about what happens when you have complex roots. That's probably, like always, like usually, that's probably the easiest case. dy dt is 5x plus 2y. So let us find out the characteristic equation by setting 0 equal to the determinant of a minus lambda I. Well, here is a 6, negative 1, 5, 2. 6, the understood negative 1, the 5, and the 2. And all I do is I go to the diagonal entries and I take away lambda. So it'll be that product, which is the same as lambda minus 2 times lambda take away 6, minus that product, which is negative 5. So it becomes plus 5. We have lambda squared minus 8 lambda plus 12 plus 5 is plus 17. So A is 1, B is negative 8, and C is 17. So lambda is negative B plus or minus the square root of B squared. You square that, you get 64. Minus 4 times 1, which I won't even bother multiplying by 17, by C. All over 2 times 1, which is 2. We have 8 plus or minus 64 minus 68 over 2. But 64 minus 68 is negative 4. You have 8 plus or minus the square root of negative 4 over 2. But the square root of negative 4, well, the square root of 4 is 2, but since it's negative, it's 2i. This division gives us 4 plus or minus. That division gives us 1i. So lambda is equal to 4 plus or minus 1i. That's called A, or alpha, and that's beta. Okay, now we need to, and this probably isn't all that easy, we need to find the eigenvector. We found the eigenvalue. Now we want to find the eigenvector. This is A, and we want to compute A minus lambda. So we need to take away you can just use one of them. Say 4 plus 1i. 4 plus 1i. These are two numbers. And a lot of times when I ask students, like let's look at this one. I don't want there to be i's involved. A lot of students say, yeah, that's two numbers, 4 and 2. No. This does not equal 4, and I meant to say square root of 2. It doesn't equal square root of 2. So what do I mean by that represents two numbers? Well, is one number with the plus, and is one number with the minus. Up here, yeah, 4 plus or minus 1i. That means 4 plus 1i, 4 minus 1i. It's two numbers. You can use, say, 4 plus 1i. Now, we want this augmented with 0. We want to solve that. Well, first let's do the math. 6 take away 4 is 2. Don't forget to take away I. Minus 1, 5. 2 take away 4 is negative 2. But please don't forget to take away the I. Okay. Now, if you multiply the first row, 2 minus I, by 2 plus I, you'll get 2 squared minus I squared, which is 2 plus 1, because I is negative 1. And 4 minus a negative 1 is 4 plus 1. So if I multiply the first row by 2 plus I, I'll get a 5 in the first position. If I multiply each entry by 2 plus I, I'll get 5 minus 2 plus I, 0. And the second row is just what it is. Let's actually distribute the minus. It'll be minus 2 minus I. Now when you subtract, the row is zeros. So the first row, I'm not changing. But the second row is just going to become a row of zeros. Now, how did I know that was going to work? The answer is I didn't. I had 2 minus I and I had 5. I want them both to look the same. I want them both to look the same. So I figured that if I multiply this by the conjugate, I know I get a real number. Because whenever you have a plus bi and you multiply by a minus bi, you're going to get that squared plus you're going to get that squared. And a squared is a squared, and b squared times I squared is negative 1. You're going to get a squared minus b squared. But always, the a and the b are real numbers. A is 2, b is 1. A is 2, b is 1. B is being multiplied by the I. The a and the b are real numbers. So you end up with a real number. And if that real number would have been 4, well then this would be 4 and that's 5. I would get them both to be 20. But I lucked out. It turned out not to be 4, but it turned out to be 4 plus 1 or 5. Which is exactly what the second row was. Okay, so now we could solve this equation. So this is K1 and this is K2. So we have 2 minus I times K1 minus K2 equal to 0. That means 2 minus I times K1 equals K2. We have that. Now, you pick a value. Let K2 be 1. Excuse me. Let K1 be 1. Let the complicated side take on a value. This is simple. It's K2. Well, if that's K1, then 2 minus I times K1, which is 2 minus I times 1, which is 2 minus I, it equals K2. So now I have K. K is equal to K1, K2. It's 1, 2, that's the real part, plus 0, negative 1I. Remember, 2 minus I is 100% the same as 2 minus 1I. And if you add these, nothing funky is going on. You add the right side, you get 1 plus 0I, which is 1. You add the bottoms, you get 2 plus negative 1 times I, which is 2 minus I. Exactly what I have here and here. So that is how we're going to write K. And this we call B1, and that we call B2. Now once we find B1 and B2, life becomes rather simple. We have that K is 1, 2 minus I, which is 1, 2, plus 0, negative 1I. This is B1, and 0, negative 1 is B2. And so the problem is pretty much done at this point. You just have to write up the answer. We know that x1 is always, when you have complex roots, is always b1 times the cosine of beta t minus b2 times the sine of beta t. The whole thing times e to the alpha t. And we know that b2 is, just switch these two around. Is b2 cosine of beta 2, b1 sine of beta 2 times e to the alpha t. And the minus now becomes a plus. So we're ready to write down what x1 is. It's b1, which is 1, 2, times the cosine of beta is 1. 1 times t is t. Minus b2, which is 0, negative 1, times the sine of beta t, 1t. All times e to the 4t. And x2 is equal to b2. So basically these two just get switched. 0, negative 1, cosine t, and plus 1, 2, the sine of t. All of this is times e to the 4t. So let me just get rid of this. So it's a recipe. Once you get the alpha and the betas, it's okay. Once and k. Your whole job was to get lambda, so you know a and b, and then define k. And separate k into the real part and imaginary part. The real part is b1, imaginary part is b2. Now, I suspect, say in our textbook, they would write down x1 is equal to, you have 1 cosine t minus 0 sine t, which is just cosine t. In the bottom, you have 2 cosine t's plus negative minus 1 is plus 1 sine t, plus sine of t. And this gets multiplied by e to the 4t. And x of 2 is equal to 0 cosine t plus 1 sine t, which is just 1 sine t. In the bottom, I like to write positive things first. You have positive 2 sine t minus cosine t. And this is multiplied by e to the 4t. So, what will the final answer be? Be very routine. X bar will equal to c1x1 plus c2x2. That is, x bar is equal to c1 times this cosine t, 2 cosine t plus sine t. That's a matrix times e to the 4t plus c2 times x2, where this is x2. Sine of t, 2 sine of t minus cosine t times e to the 4t. And there is the final answer. Okay. Let's try one more where we have complex roots. So we did 2. Let's try one more with complex roots. Suppose you were given the problem x prime is equal to some matrix times x, and you want to find x. Now, you need to compute, you define the characteristic equation. 0 is equal to the determinant of a minus lambda I. Well, A is this matrix. If you take away lambda I, that just means you take away I from the diagonal. And since it's a 3 by 3 matrix, it has 3 rows, 3 columns, we repeat the first column at the end, and then the next column, the second column at the end. And the determinant is going to be one sum minus another sum. It's going to be this product, 1 minus x to the third power, plus that product, which is 0, plus that product, which is 0, minus this product, which will be negative 2 times 1 minus lambda, plus that, plus 1 times 1 minus lambda. So what we're going to have in the second bracket will be negative 1 minus lambda. I mean, we're adding 1 minus lambda. You have negative 2 and you add 1, you have negative 1. And this negative, the subtraction is going to become addition, and the sign of the negative 1 minus lambda changes. So what we have is 0 is this, 1 minus lambda cubed plus 1 minus lambda. And we could factor this. We can even call it the u cubed plus u, where u of course is 1 minus lambda. You can factor out a u, and you get u squared plus 1. So if it equals 0, that means either u is 0 or u squared plus 1 is 0. That means u would be plus or minus I. So u, which I'm going to write this way, is 0, or u is plus or minus I. Well, of course we know what to put there instead of lambda. We put 1. 1 minus 1 is lambda. So lambda is 1. We can interchange these two. The 1 stays. The plus I comes over as minus I. The minus I comes over as plus I. The lambda goes over as lambda. So instead of minus plus, we'll write plus minus anyways. So we have 3 roots. One real root, 0, of multiplicity of 1, and another 2 roots, 1 plus or minus 1i. So now we need to find, let's deal with the lambda equals 1. So let me just put some silly subscripts down, 1 and 2. So now when lambda is equal to 1, we need to solve our famous equation, a minus lambda I, and 1 times I is just I, so just a minus I times k is equal to 0. We want to solve that equation, the 0 vector. Well, a minus I, well, from the diagonals, you just take away 1. So the diagonals will actually become 0, and every other entry will be what it is over here. We want to augment this with 0. Now, this matrix is pretty much done. There's not a lot of magic there. If we subtract the last 2 rows, let me do more than that. Let me multiply row 1 by negative 1. So I'll get 0, 1, negative 2, 0. Row 2 I'll multiply by negative 1. And row 2 and 3 are the same, so when I subtract them, I get zeros. So row 1 tells me that 1 times K2, 1 times K2 minus 2K3 is 0. Bringing this over, K2 is twice or 2 times K3. So if we know K3, we multiply it by 2, and like magic, we get K2. The second equation tells us that K1 is 0. Well, how about I just pick some value for K3? Say it's 1. So then K2 will be 2 times 1, or 2. So now I know K is little k1, little k2, and little k3. Now I have k. So then x1 will be k1, times e to the lambda t, e to the 1t or just t. So k is 0 to 1. K1 is 0 to 1. And x1 is 0 to 1 e to the t. Okay, now we deal with lambda 2. We want to find what k is. So we want to compute a minus lambda I times k is equal to the 0 vector. So here is a, and from a, I'll take away, I'll call it 1 minus I. I could have used 1 plus I. I'll show you why I used 1 minus I. Now 1 take away 1 is 0. Let's not forget to take away negative I. That gives us plus I. If I would have had 1 minus 1 plus I, fine. That 1 minus 1 would have been 0. But then I would take away I, and I would get negative I. I don't want negative I just want I. Now, all the diagonals are the same. So when we do those 3 calculations, we better get the same answer every single time. I. So this is basically augmented with 0. We want to solve that. Now, I'll do this over here. If I multiply row 1 by I, when I multiply that by I get negative I. If I multiply that by I get negative I made one mistake. If I multiply this by I get negative 1. Multiply that by I get 2I. Multiply that by I get 0. In the second and the third row, I'm not going to change yet. Due to space constraint, this is gone. Now, I'm going to leave row 1 the same, but then I'm going to do row 2 minus row 1. That minus that is 0. That minus that is 2I. That minus that is minus 2I. 0 minus 0 is 0. Now, I can divide by 2. and I'll have 0i, negative I. Row 3, I'm going to do row 3 minus row 1. That minus that is 0. 0 minus a negative I is I. I minus 2i is negative I. Now the first two rows I'm going to add. I add those two. I add those two to get the 0 that I wanted. I add those two, and 0 plus 0 is 0. The second row, I'll multiply by negative I. 0 times negative I is 0. I times negative I is 1. Negative I times negative I is negative I. Sorry, is negative 1, I meant to say. And 0 times negative I is 0. Now, the second and third row, I'm going to subtract. And that'll be the new row 3. 0 minus. They're actually, row 2 and row 3 are the same. So when I subtract, I get 0. Nice and quick. Now, for row 1, I'm going to multiply by negative 1. So I just get that. What I get is k1 minus I times k2 is 0. That means k1 is I times k2. Let k2 be, say, 1, then k1 is equal to I times 1. Or let k2 equal I. Second equation tells me that k2 minus k3 is 0. That means k2 equals k3. So how about I let k2 equal 1? Well, that would mean that k3 is 1. And it would also mean that k1 is I. Because k1 is I times 1. Because k2 is 1. So then what we have is that k, call it k2, is equal to little k1, little k2, little k3. Now this we want to break up into the real parts and the imaginary parts. The real part is 0, 1, 1 plus 1, 0, 0, I. Why is that? Because the I in the first position is really 0 plus 1i. 0 plus 1i. That 1 is 1 plus 0i. This one here is 1 plus 0i. And this one down here is also 1 plus 0i. 1 plus 0i. The real part is called B1. The imaginary part is B2. And for the lambda, the real part is alpha, and the imaginary part is beta. Now it's rather easy to write down what K2 equals. It's rather easy to write down what X2 equals, I meant. Well, X2 is equal to B1 cosine of beta, which is 1t. Beta t, 1 times t is t, minus b2, which is 1, 0, 0, times the sine of beta, 1t. 1t is t. And x3 would be b2, 1, 0, 0, times cosine of t plus b1, 0, 1, 1, times the sine of t. So this is really equal to 0 cosine t minus sine t, which is minus sine t. 1 cosine t minus 0 sine t. I won't write that. Plus 1 cosine t minus 0 sine t. I won't write that. Same thing with the bottom. Is 1 cosine t plus 0 sine t. 0 cosine t, which is 0, plus 1 sine t, sine t. Same with the bottom one. So now, and this needs, x2 needs to be multiplied by e to the alpha, which is 1, alpha t, e to the t. Same thing for the bottom one. So the solution is going to be c1 times x1. There's x1. Zero, 2, 1, e to the t, plus c2 times x2. This is x2. The matrix, negative sine t, cosine t, cosine t, all times e to the t, plus c3 times x3. That's x3. Cosine t, sine t, sine t, times e to the 1t. There's the answer. You plug that answer in right here, right there. Multiply this matrix times this x, and you will get the derivative of that x. And you will get the derivative of that x. This completes this section. Do lots of problems as it's doable.